Good evening, ladies and gentlemen. How is everyone doing? I'm also well, thank you. So let's wait for another minute or two and see who else joins us. But I'm glad to see that the regular cloud is online. So lots of deadlines. So deadlines for assignments, tests, or everything. I see everything. So in the life of a student, there's always something new, always something that needs to happen, and everything requires good time management. I'm glad. So all of a sudden in this class, it's usually if there's a subject being complained about, it's course 151 or WTW 114, 115. So I read that Greece and Uruguay are the only countries with astronomy in high school. Do you think astronomy should be taught in high school? Yes, I believe so. I believe if in high school if you can teach different subjects or there's a subject selection that astronomy is a good aspect, or even if there's a chapter in natural sciences in high school about astronomy. I know in some private schools they have an option for it, but not everywhere. So I'm really impressed that some schools teach astronomy on high school level, but some schools also has astronomy clubs. So it sucked that you never did it in high school. That's interesting. So it seems like there is a little bit of astronomy then. So have you guys worked through the mock semester test I uploaded? So would you guys like me to go through some of the answers? Okay, so let me share the mock semester. So during tonight's lecture, if you have questions on the work covered, we can go through it again. But for tomorrow night's lecture, half of tomorrow night's class, I'm going to dedicate to questions about the semester test. So I'm going to ask you guys to provide me with the answers. And if you want me to explain something, I will explain something. But the idea for the mock test is that you sort of create your own memo and have your different friends in the class help you with it. And to clarify, yes, the test is going to be online. So what I would like you to do is with the test, you have one tab. Yes, try to zoom in. It's going to be difficult to zoom in on my side because on my side it's going to zoom but not for you. Well, one thing I can do, let me do this, I'm going to open up in a different application window. So I think it's going to be a little bit easier, then I can zoom in. So let me do it this way. Then I can zoom in. Okay, so you should be able to see my screen. Awesome. So the test is going to be multiple choice. It's going to be an online test on Blackboard. So what I would like you to do is to open up the test in one tab and open up Blackboard Collaborate in a different tab. So if you have problems, questions, if there's technical difficulties, you can just unmute yourself or type in the chat and I'm immediately to help you guys. Awesome. So for the test, it's going to be 50 minutes, 2.5 hours. So it's more than enough time needed. So for 50 minutes, so for 50 marks, multiple choice, hour and a half is an appropriate time, but I allocated 2.5 hours for you guys, so it's more than adequate time. Just make sure you read the questions carefully, make sure you read the options correctly. And the test will be on the same difficulty level as this mock test. So for question 1, the average distance from Venus to the Sun is what? And why do you say B? Yes, so Earth is one, that's the correct way of arguing. So Earth is 1 AU away, so it must be less than 1 AU. And Mercury is about 0.5 AU. So yes, the correct answer is B. Then question number 2. Our Milky Way galaxy has a diameter of 75,000 light years. How long does it take to cross the diameter of the galaxy? And why did you guys say D? Yes, exactly. 1 year, 1 light year is 1 year, so 75,000 years. Then question 3 is basically just straightforward arithmetic. So if light takes 8 minutes to reach Earth from the Sun and 1.3 hours to reach Saturn, what is the distance from Sun to Saturn? C is correct. Are you guys comfortable on how you got to C? Okay, so I'm going to ask the class, because I wanted to keep this a discussion, are there any volunteers perhaps that wants to demonstrate how the arithmetic works? Okay, so what I'll do is, for now, I'll make all of you make you presenters. So then you will access to the whiteboard. So presenters, going to make you all guys presenters. So I don't know why this option I can make you all presenters at the same time. See what I can do. So it looks like I have to do this by hand, but that's not a problem. If you just bear with me, I'm just making you presenters. So if you are now made a presenter, you will see there's a few more options available where you can share your screen and you can also access the whiteboard. This is a tedious work now, but we'll have to do it this way. Half the class is now presenters. Almost there. No, this is tedious and taking time, so I will set up the session correctly from beginning next time. Okay, 24 to go. So if we were in a lecture venue right now, I would actually ask volunteers to do this on the board in front of the class, but unfortunately we are not in a lecture hall right now. So this is the best we can do currently. 12 left. Okay, so everyone should be presenters now. So let's go through the arithmetic. If light take 8 minutes to reach Earth from the Sun and 1.3 hours to reach Saturn, what is the distance from the Sun to Saturn? Mr. Elsden, I will just make them a presenter again. So let's go through what you did. So 1.3, so 8 minutes equal 1 AU, that's correct. So 1.3 times 60 equals 78 minutes. Divide by 8 gives 9.75 AUs. That's correctly it. So just play forward straight arithmetic. So the answer is correct, C, 9.75 AU. So in textbooks, you'll usually see the number is usually rounded to 10 AU. In question number 4, the apparent visual magnitude of a star is 7.3. This tells us that a star is what? Why do you guys say C? Yes, you guys are correct. The human limit is magnitude 6. So yes, the answer C is correct, not visible with the unaided eye. Then question number 5. An object has been located orbiting the Sun at a distance from the Sun of 65 AU. What is the approximate orbital period of this object? Yes, Mr. Andreas Visagi, number E is correct. How did you conclude it was number E? So, do you guys have any other ideas? So if you have no other ideas for this, let's keep this question open for tomorrow evening, then it will show the calculation. And just a little bit more time for you guys to think about it. But question number 5 is probably the most difficult calculation you'll do for the semester test. So question 6. The star Alpha CMA has an apparent visual magnitude of minus 1.46, and a star Alpha Set has an apparent visual magnitude of 12.53. Both stars are the same direction from Earth. This tells us what? Okay, so I see here, yes, number B is correct. So why do you guys say number B? Yes, that's correctly how you argue. So from this information given to us, we know that alpha CMA has an apparent visual magnitude of minus 1.46, meaning its apparent visual magnitude is higher than minus 2.53, meaning more energy is produced by alpha CMA. So that's correct. Then question number 7. The table below lists the spectral types of 5 stars. Which one has the greatest surface temperature? Why do you guys say number E? Yes, bingo. I'm glad one of you remember Oh Be a Fine Guy or Oh Be a Fine Girl, Kiss Me. Well done. So question number 8. Most of the light we see coming from the sun originates where? So question with the numbers after the letters. Want to start. So when we have these classification in stars, if we have a O0 and an O1, the O0 will be hotter than an O1, and an O1 will be hotter than an O2, and an O2 will be hotter than an O3. So for example, if we have an M6 and an M5, M5 will be hotter than an M6.
So,
Yes.
do the numerical values tell us about the size of the star?
Uh, a little bit. So if we have a O-type classification, it's on a family of stars. So all O-type stars are roughly the same size and temperature, but that's why we have sub-classifications such as O0 or A0 to 9. So it tells us, so for example, if you take an A2 and an A3, the A3 has a little bit more energy, so it will be a little bit cooler, and therefore its size will be a little bit smaller.
Thank you, sir.
Pleasure. Something off topic, while we're speaking about star classifications, my nerdy side is coming out again. So for those of you that are Star Trek fans, you will realize they use this classification when they're entering a star system. The helmsman or the person operating the con will usually tell it's what type star it is. So I thought you guys would find that interesting. So a B0 star is still called then an O star. So if we see an O star, we know straight away it's hottest. Yes, that's exactly it, Mr. Els. Pleasure, and something else I've discovered over the weekend I was quite impressed about. Um, I downloaded on Steam the game EVE Online. That's basically a MMO for space exploration and everything. So I'm actually quite impressed with the game because in the game they have distances correct, they have AU, they use AU, light year, parsec, they have star classifications correct, they have planet classifications correct, their orbital characteristics is correct. So I'm impressed with it. So I started playing it and I'm enjoying it so far. So going back to the questions. So question 8. So you guys say B. Why B? Yes, Mr. Labuyo.
So because under the photosphere, so everything is much. I mean, the photosphere is dense enough so that light produced from the bottom can't necessarily come up, and above the photosphere, which would be the chromosphere and the corona, though the gases there is not as dense as the photosphere, and so that can't necessarily produce enough light so that we can see.
Yes, that's correct. So Mr. Groenewald is spot on. This photosphere is the lowest layer of the sun's atmosphere. Yes, and that is why we see most of our light coming from this photosphere. In question number 9, star A has an apparent visual magnitude of 15.4 and star B has an apparent visual magnitude of 12.4. This means that star A is what then star B? Okay, so I see 2 people voting for C, 1 person voting for A. So, which one is it, A or C? So I see a lot of people vote for A, but the correct answer is C, 16 times fainter. Mr. Roberts, I'm putting you on a spot, but are you willing to go through the calculation or explain the calculation? Or Mr. Luca Loepscher? If mic doesn't work, you're more than welcome to use the whiteboard or the chat function.
Can you hear me?
Yes, I can hear you.
Okay. So using the function if FA over FB, I just switched the names of the stars around, so I changed it to FB over FA is equal to 2.51 to the power of the visual magnitude of B minus the visual magnitude of A. So it's 2.51 to the power of 15.4 minus 12.4.
That's exactly it. That's bingo. Straightforward application of the equation. Perfectly explained, guys.
Thank you.
So yes, from this, we can determine that star A is 16 times fainter. So this is just another point I'm going to make that's a bit off topic, but usually somewhere during your line, you will hear some lecturer moaning about make sure you choose your directions correctly, especially when it comes to circuit analysis and electron flow. Don't worry about it. The math will get you to the right answers. So usually when you get a negative answer, it means your assumption was wrong. It's actually the other way around. So math in these types of questions are your friends. And here the math tells us that it's 16 times fainter. So why is it fainter? So you can see we have an apparent visual magnitude of 15.4 and an apparent visual magnitude of 12.4. So from this magnitudes, we can already see that Does someone want to jump in? Okay. So from this already, we can see star B is already brighter than star A, but we don't know by how much. And by doing the calculation, we can see that star B is 16 times brighter, or star A is 16 times fainter. So are we allowed to make a formula sheet? So there are not many formulas for this module. I think we'll have 5 or 6 formulas at the end, so technically you are not allowed a formula sheet. But let me ask you guys this way. Since we are only 62 people in the class, I would like to give you guys a fair chance. Would you like me to provide you guys with the formula sheet? Okay, I'll provide you guys with a formula sheet you can use. That's a good idea. Perhaps in the test instructions, that's a good idea. I will add it in the test instructions. Then, so one thing, that's why I don't mind giving formula sheets. For me, is it if you are a good scientist or engineer, computer scientist, systems designer, it doesn't matter where or what the formulas are. You don't need to memorize formulas. As long as you know how the formula works and where you can find a formula, then you are all set. So question 10, the what, is, or are the hot gases that are the moving extension of the sun's corona? So why do you guys say E? So why do you guys say number E? Any idea, guys? Why is everybody so quiet now?
So can I object and say that it's not E?
Yes, you can object.
So I want to say it's not E, sir, because solar wind is when when it's a corona hole, and then it's like most of the ionized gas from the from the lower levels of the corona.
So that is also correct. So what is the answer? So let's debate this a little bit.
I would say A, sir. I would
So
say
you would
A.
say A.
Yes.
Okay. And the rest of the class? So yes, Mr. Groenewald, so gas flows away from the sun. So Because the spicule is like a jet stream, yes. And X-ray gas moved away by magnetic fields, yes. So the correct answer is number E. It is solar wind. So, Mr. Groenewald, ionized low-density gas cannot cross magnetic fields. So when the sun's field loops back to the surface, gas is trapped. However, some of the magnetic fields lead outward into space, and so gas flows away from the sun. So, sir, can you explain what it is, this question? So, the what is the hot gases that are moving extensions of the sun's corona? So the correct answer is the solar winds. So remember, yes, Mr. Levuyo.
So why would it be the solar wind, sir, if sir, the solar wind is something that leaves the atmosphere of the sun?
So yes, that is true. The solar winds leave the atmosphere of the sun. So let me think, what's the best way to describe it? Okay, so best way will be, let me get the whiteboard. I like using the whiteboard. So if this is the sun, the spicule will be a filament that does this, and another filament that does this. So in theory, all matter leaving will go back to the surface of the sun. But if we have a solar wind, it's gas that leaves the sun. And that gas that leaves, that forms part of this, is in the corona of the sun. So therefore, the moving part of the corona is solar winds.
But then, sir, don't solar winds extend further out into like out of the solar system? Because then I don't think you would be able to say that the sun extends out to the edge of the solar system.
No, the sun doesn't extend. So what happens is with a solar wind, so it's a piece of the sorry, I mean promises. Yes, you are correct, Mr. Robert. Sorry about that. My mind is at a lot of different places this evening. So the solar wind is pushed out of the sun. It's part of the corona, and the further it moves away in our solar system, it loses energy. So solar winds never reach planets like Uranus, Neptune, because they are too far out, but the innermost planets are affected by solar wind.
So then, so where would the what is it called? The limit of the corona, where would that be? Because you saying that the solar wind can extend to at least where Earth is.
Yes, because remember, solar wind, so the corona is a fixed area around the sun. But pieces of the, you think about it, let's visualize it as pieces are blown away. So let me, what's a good example I can use to explain this? So we can visualize this easy. What is a good example? So a good example is, so let me draw it. So yes, that could heat up a fire. We can use that as a good example. So what we can use as describe solar wind is we have the sun. Then around the sun, we have the corona. But we can think about this as, let's for just, for example, all intents and purposes for this example, you can imagine this as some sort of a wind. And that sort of wind will take a chunk of the extension of the corona. And you can imagine it almost as breaking this chunk loose and then blowing it towards Earth, that is over here.
So basically what you're just saying is just there's still solar wind within the corona. It's just that where there's a corona hole, it just leaves.
Yes.
Okay. Okay. Thank you, sir.
It's a pleasure. So let me share the screen again. Okay, so question 11. When we say that gravitation is universal, what do we mean? And why do you guys say number E? Number E is correct, but why do you say number E? Yes, it all comes, Mr. Groenewald, you're correct. It all comes down to Newton's gravitational law. Then question number 12. To determine the radius of a distant star, we need to know its what? And why do you guys say number D? Number D is correct. It's temperature and luminosity. So remember, we learned if we know what the temperature and luminosity of a star is, we can learn a lot of its characteristics and its physical characteristics. So temperature and luminosity is very important, and we learn from the magnitude scale that we can get the temperature and luminosity. In question number 13, the force of gravity between two objects depends on what? So yes, Mr. Groenewald, bingo. Everything is encapsulated on the HR diagram. And for this, everyone is correct. The answer is number D. So the force between two objects depends on the mass of each object and the distance between the objects. And that is where the inverse square law becomes interesting on effects. So unfortunately, I'm not going to post the memo. So the idea is that you guys that attended this lecture will have access to the memo, will be able to see the memo, I'll be discussing it, and people watching recordings and everything. So from 100 odd 150 students, only 59 is online right now. And for those people not looking at everything, I don't want to spoon feed them and basically give everything on a silver platter, but where you actually sit in class, you actually put effort into it, you guys deserve to have extra help. So that's why I always say the last 2 weeks, it's the regular crowd that's online. So on a different note, for the preparation for Wednesday, if you have questions or something you need to explain in the next 2 days, I will be available via email, WhatsApp, Discord, as long as it is within reasonable hours, because I still need to spend a bit of time with my family and do a bit of my own work. So as long as it is within reasonable hours. And you don't have to be shy. If you would like to set up a consultation, then we can set up a Zoom, Skype, Google Meets, WhatsApp call, whatever you need to help you. There were 2 students already that set up consultations with me. I have an open door policy. So if you were on campus, I would have an open door policy, meaning you don't need a consultation appointment. You can just pop in any time and I will help you. But unfortunately now with COVID, that's a bit more tricky. So I'll be available on all platforms to help you guys as long as it is within reasonable hours. It's a pleasure. So if you have any, want to set up consultations, sessions, anywhere from now to before the test. The mornings I usually have meetings scheduled in the morning. So tomorrow morning I have meetings scheduled until about 11. But after that I'm free, and Wednesday I have no meetings scheduled yet. So if you want a consultation session, just please contact me and we can organize one. So question number 14. On the HR diagram, white dwarfs are found where? Yes, D is correct. And why did I say number D? Yes, very high temperature and low luminosity. Then question number 15. Absorption lines due to interstellar medium indicate that some components of the interstellar medium are cold and of low density because so what do you guys say, D or A? Let's debate this a little bit. D or A? So there's a slide I specifically in one of the slides I explain this. So I'm just going through my notes quickly to see if I can explain this to the best of my abilities. Just hang in with me so I can try to find it. Okay. So remember in our slides, And I also spent a little bit of time on it on Kirchhoff's laws. So, Mr. Bekus, you checked the slides, so I'm putting you on the spot a little bit, but why is it number D? I'll quickly see if I can find that image I showed in class. Where do I say I have a nice image? So, Kirchhoff laws, I'm going to share this. Let me see if I can quickly share this image. So here, in this image, we can see a continuous spectrum, an emission spectrum, and a absorption spectrum. But it all depends on what is in the background. So the object we are observing, what is happening in the background. So if we go back to our slides, share application screen. So here we can see absorption lines due to interstellar medium indicate that some components of the interstellar medium are cold and of low density. So the lines are blue shifted, the lines are red shifted. So these two we can automatically cancel out because we are looking at absorption and emission and continuous spectrum. So now is where things start to become interesting. So the lines are extremely broad, the lines are extremely narrow, and then the lines are much darker than the stellar lines. So the hint was, it's on lecture 10. So Mr. Bekus said interstellar spectral absorption lines can be recognized because they are very narrow. Yes. Only photons with energies exactly equal to the energy difference between two energy levels can be emitted or absorbed. Yes. And because we are looking at the interstellar medium, the lines are recognized as extremely narrow lines. So the answer is number D. Then Ms. Niemand, this test will be move on and come back to question if you struggle with it. Yes, you will be able to move between questions. I will make sure that functionality is activated. Then question number 16. The Copernican system was not accurate in predicting the positions of the planets because yes, number C is correct. It made use of uniform circular motion. Question number 17. Galileo's telescopic discoveries of the moons of Jupiter proved what? Don't worry. Usually you will see there's a trade-off between sciences and language. You can do science but not spell. So yes, number C is correct. Then question number 18. A solar or lunar eclipse will occur when?
Sir,
Yes.
going back to that other question, sir. The answer was C because you said the Earth can't move without its moon.
Yes.
But then,
the Earth can move without leaving its moon behind, meaning the moon orbits Earth.
so wasn't that always the idea that that everything in the solar system orbits around the Earth?
So yes, that was the idea. But remember, we know from this, you can put it in not in an Aristotelian universe, you're right, Mr. Loebscher, but you can also put this in another way of thinking. So we know the moon orbits or goes around Earth, but that's the first time we see another object orbiting around another planet.
Yes, sir. And so because of that, sir, I forgot who it was, but then they were that person was the one that said that we are that we orbit around the
Sun.
yes. So then, so
Yes,
wouldn't Galileo's observation show that not that our solar system doesn't necessarily revolve around the Earth, but other bodies can orbit around one another and not specifically the Earth, and therefore you can say that Jupiter orbits around the Sun as well.
Yes, so that's the correct way of arguing. So this is a short and sweet where this answer leads up to.
So then, so wouldn't B be the answer and not C?
Jupiter orbits the Sun, but from the Aristotelian universe, we know it was imagined that everything orbits Earth. But this is important to realize because this question, I'm trying to ask this question coming behind, does the moon orbit the Sun or does the moon orbit the Earth? So one of the discoveries that Jupiter's moons orbits Jupiter means that Earth's moon must orbit Earth and not the Sun.
Yes, sir.
Okay. So back to question 18. A solar or lunar eclipse will occur when? Okay, so I see here A and E. So which is the correct one? Which would you say is the, so let's debate this also a little bit. So the correct answer will be number A. So those people that said A, why is it number A? So yes, you guys are correct. So we will need the sun and moon to line up. So one must be in front of the other one. So that is why when the sun is near the line of nodes of the moon and the moon is new or full. Okay. So let's go to the nodes. So drawing this now, we will have the sun over here. We will have Earth over here. And we will draw the moon over here. So the nodes that we have will, so everything orbits the sun. So let's see if I do this way. And let's get a different color. The moon orbits Earth. So when everything is lined up, so yes, the places where you are correct. So let's see, Mr. Grunewald, for an eclipse to occur, the moon must be passing through the plane of Earth's orbit. The places where it passes through Earth's orbit is called nodes. So yes, that is correct. So this is not drawn entirely to the best of my abilities, but from here we will see, so this will be a node and this will be a node. So meaning from here, if it passes through these two nodes, depending where you are located on Earth, this will make a sort of a cone shape. This is way too big, but it will give the idea that depending where we are, we will either have a lunar eclipse in this area or a solar eclipse in that area, depending where we are. So the correct answer is number A. Then the last question for this mock test is, star names are what? Aha, so I see a lot of replies now. Sorry, I'll go back to ecliptic question after this one. So let's do question 20 first, since a lot of people has answered. But yes, the correct names, a lot of star names are Arabic. So let's go back to question 19. The ecliptic is what? So C is C, D, and B. So which is the correct one?
Sir, could you please explain what they mean by projection of Earth's orbit?
Okay, I'll come to that now. So before answering that, so let's debate this. So let's debate this among each other. Why? Why are you choosing that specific answer? Any volunteers? So you have a lot of options. So defend your option. But is the ecliptic not related to the path of Earth? No. So which do you say? So the correct answer is C. The ecliptic is, oh, sorry, not C. I got mistaken. So the correct answer is number D, all of the above. Because remember, if you draw the ecliptic, the center is the center line of the zodiac. So it's the projection of Earth's orbit on the sky and the apparent path of the sun around the sky. So I can't remember which slides it was, but in the slides I created, there is a nice figure I included that shows how the ecliptic works. So this is so this will be the level of the semester test on Wednesday evening. But unfortunately, we still need a bit of work that we need to continue on with this week's lecture. So in tomorrow night's class, I'll dedicate half of the class again to answering all your questions. So if you have a list of questions, please let's discuss it tomorrow evening, or otherwise just bug me throughout the day. So last week we ended off with this slide. So for number 20, it is number C, Arabic names. Pleasure. Okay, so you say you managed to solve, let's go back to that one. So managed to solve it. So are you willing to explain it to the class? Okay, you can go ahead. You can use a whiteboard, you can use the chat, you can unmute yourself. Any way you are comfortable with.
Sorry, sir, can you hear me? I just had to plug in my earphones. There's a guy in my corridor who's playing music quite loud, so I'm not sure if you guys can hear that.
We can't hear anything. We can hear you perfectly.
Okay, excellent. Thank you so much, sir. Okay, so according to Kepler's third law, we have that a planet's orbital period squared is proportional to its average distance from the sun cubed. So we know that so we can just use the distance the planet is from, or the distance that was provided, that is 65 AU, and then we can plug that into A and solve for P, the orbital period. So then we'll just square both sides, or not square, use a square root on both sides. That'll isolate P, and then the solution ends at E.
Yes, that's correct. So can you write on this whiteboard?
I can try, sir.
Perfect.
Sorry, so that's supposed to be an A, and this is a 3. So then we'll just put P equal to square root this, A to the power of 3. Then we just plug in A for 65, and then we'll cube that. And the solution will end up with 524, which is equal to E.
Bingo! Thank you very much. This was exactly what I was looking for.
Thank you, sir.
Awesome, and this
Okay,
will be,
cool.
so this is probably going to be the most difficult calculation for the semester test.
Okay, that's good to know, sir. Thank you.
It's a pleasure. So well done. So now we have the solutions of everything to the semester test. So let me open up our slides again. So last week we ended up here, where we have the galactic plane, we have disk stars and halo stars. So when everything is in the galactic plane, the stars are disk stars. But if it's above the galactic plane in these eccentric orbits, those are halo stars. So halo stars and globular clusters, however, follow highly elongated orbits tipped steeply to the plane of the disk. So in the previous diagram is the image I'm referring to. So although the diagram shows these orbits as simple ellipses, that is not quite true. The gravitational influence of the thick bulge forces them into curves that do not quite return to the same starting point. The dramatic difference between the motions of halo stars and disk stars will be important evidence when you consider the formation of the galaxy later in this chapter. The analysis of the components of the Milky Way galaxy may leave you wondering about one important question. How much matter does our galaxy contain? And to answer that question, you measure a galaxy's rotation. To find the mass of an object, astronomers, so remember when we find the mass of a binary system, we look at the orbital periods of the binary system. So the same principle we're going to apply to galaxies. So to find the mass of an object, astronomers must observe the motion of another object orbiting it. Just as a binary star system. Humans don't live long enough to see stars move significantly along their orbits around the galaxy. But astronomers can observe the radial velocities, proper motions, and distances of stars, and then calculate the sizes and periods of their orbits. The results can reveal the mass of the galaxy. Stars in the disk of the galaxy follow nearly circular orbits that lie in the plane of the disk. Current observations indicate that the Sun orbits the center of our galaxy at about 225 kilometers per second. moving in direction of Cygnus. The evidence suggests that the Sun's orbit is nearly circular. So given the current best estimate for the distance to the center of our galaxy, 8.3 kiloparsecs, you can find the circumference of the Sun's orbit, multiplying it by 2. If you divide the circumference of the orbit by its orbital velocity, you will discover then that the Sun has an orbital period of about 225 million years. So doing this from memory and thumbsucking it means that our Sun, the Sun has orbited our galaxy in about 8 galactic years. So the radius of the Sun's orbit around the galaxy is about 8,300 parsecs, and each parsec equals 2.1 times 10 to the power 5 AU. Multiplying, you find the radius of the Sun's orbit is 1.7 times 10 to the power 9 AU. The orbital period is 225 million years, so the mass is 100 billion solar masses. This is only a rough estimate, because it does not include any mass lying outside the orbit of the Sun. Allowing for that overlooked mass yields a lower limit to the total mass of a galaxy, to at least 4 billion solar masses. The rotation of a galaxy is actually the orbital motion of each of its stars around the center mass. Stars at different distances from the center revolve around the center of the galaxy with different periods. So stars starting near each other will draw apart as time passes, a situation called differential rotation. So in this image, we can see the differential rotation of the galaxy means that stars at different distances from the center have different orbital periods. In this example, the star just inside the Sun's orbit has a shorter period and pulls ahead of the Sun, while the star outside falls behind. So we can also see this in our own solar system. The planets closer to the Sun orbits faster around the Sun, and the planets further from the Sun orbits slower around the Sun. To fully describe the rotation of our galaxy, astronomers graph orbital velocity versus radius to produce a rotation curve. So this here is an example of a rotation curve. The rotation curve of our galaxy is plotted here as orbital velocity versus radius. The data points show measurements made by radio telescopes. Observations outside the orbit of the Sun are much more uncertain, and data points scattered wildly. Orbital velocities do not decline outside of the orbit of the Sun. As you would expect, most of the mass of the galaxy were concentrated towards the center, so Keplerian motion. Rather, the curve is approximately flat at great distances, suggesting that a galaxy contains significant mass outside the orbit of the Sun. If all the mass of the galaxy were concentrated near its center, you would expect to see orbital velocities decrease as you move away from the center. That is what you should see in a solar system, where nearly all of the mass is concentrated in the Sun. For this reason, this is called Keplerian motion, referred to Kepler's laws. In contrast, the best observations of the rotation curve of the Milky Way show that orbital velocities in the outer disk are constant or even increasing with distance from the center of the galaxy. Those high orbital velocities indicate that the larger orbits enclose more mass and imply that our galaxy has much more mass than is contained within the radius of the Sun's orbit. Both observational evidence and mathematical models show that the extra mass lies in an extension halo, sometimes called a galactic corona, that may reach out to 10 times further than the edge of the visible disk and could contain more than a trillion solar masses. Most of that mass is invisible, neither emitting nor absorbing light, so astronomers refer to it as dark matter. Some of the mass in the galactic corona is made of low luminosity stars and white dwarfs. but much of the mass must be some other form of matter. The most striking feature of galaxies like the Milky Way is their patterns of spiral arms that wind outward through the disk. These arms contain swarms of hot blue stars, clouds of dust and gas, and young star clusters. The young object suggested that the spiral arms involve star formation. But as you try to understand the spiral arms, you need to consider two problems. Firstly, how can anyone be sure our galaxy has spiral arms if interstellar dust obstructs our view? Secondly, why doesn't the differential rotation of the galaxy destroy the arms? Then lastly, the solution to both problems involves star formation. As you have already learned, O and B stars are often found in associations and are very luminous. Thus, they are easy to detect across great distances. Unfortunately, at those great distances, their parallaxes are difficult to observe. The available data indicate that OB associations near the Sun are not located randomly, but lie along several spiral arm segments. So near in image A, we can see nearby young O and B stars in our galaxy fall along bands that appear to be segments of spiral arms. In image B, many of the galaxies in the sky are disk-shaped like our galaxy. Most of the galaxies have spiral arms marked especially hot, luminous stars, and emission nebula that must be very young. This might cause you to suspect that spiral arms are related to star formation. And in image C, images of other galaxies show spiral arms that are especially prominent and well defined. Those spiral segments have been named for the prominent constellations through which they pass. Astronomers can now use infrared and radio telescopes to penetrate the interstellar dust, locate more distant OB associations, and trace the spiral arms even further. Objects used to map spiral arms are called spiral traces. Aside from OB associations, spiral traces include young open star clusters, clouds of hydrogen ionized by hot stars, and certain higher mass variable stars. Notice that all spiral traces are young objects formed recently. Astronomically speaking, O stars, for example, live for only a few million years. Their typical orbital velocity is about 200 kilometers per second, so they cannot move more than about 500 parsecs in their lifetimes. This is less than the width of a spiral arm. Because they don't live long enough to move away from the spiral arms, they must have formed there. Studies of other galaxies show that their spiral arms are also marked by hot blue stars and other spiral traces. The youth of spiral traces is an important clue about spiral arms. Obviously, spiral arms are associated with star formation. Before you can follow this clue, you need to extend your map of spiral arms to show the entire galaxy. So here we can see our image again, and here we can see our traces. Here is our own sun. So the Perseus arm, the Orion Cygnus spur, the galactic center is this way, and this is the Sagittarius arm. Radio astronomers used a strong spectral line emissions from carbon monoxide to map the location of giant molecular clouds in the plane of the galaxy. So the dust that blocks our view at visual wavelengths is transparent to radio waves because radio wavelengths are much larger than the diameter of the dust particles. Recall from Chapter 9, Section 2, that giant molecular clouds are sites of active star formation. If you point a radio telescope at a section of the Milky Way, you will receive a combination of signals from gas clouds in the direction you're looking that lie at various distances across the galaxy. Signals from those different clouds can be separated by measuring the Doppler shifts of the spectral lines. Astronomers then use a simple model of orbital velocities at different distances from the center of the galaxy in order to untangle the observations and locate the individual clouds. Maps constructed from such observations reveal that giant molecular clouds like O and B stars are located along segments of spiral arms. In this image, we can see an image A. At a wavelength of spectral lines emitted by carbon monoxide molecules, astronomers find many molecular clouds along the Milky Way. But the clouds overlap in a confusing jumble. By using a model of the rotation of a galaxy to interpret the radial velocities of the clouds, astronomers can estimate the distances to each cloud and use them to map spiral arms. Then in image B, this map represents the view from a point 2 kiloparsecs directly above the Sun. The molecular clouds shown here as hemispheres extending above the plane of our galaxy are located along spiral arms. Angle labels indicate galactic longitudes. As you learned in Chapter 9, observing at a wavelength of 21 centimeters allows detection of a spectral line of atomic hydrogen. The type of gas is generally warmer than the material in the molecular clouds. Just as for the molecular clouds, analysis of the atomic cloud radial velocity data requires that astronomers start with estimates of the orbital velocities at different distances from the center of the galaxy. The atomic hydrogen map doesn't trace as clear as a spiral pattern as the molecular gas, in part because the warmer atomic gas has more random motions due to its temperature as well as turbulence within the clouds that distort the radial velocities. Observations toward the center of the galaxy have an additional problem. There, orbital motions of gas clouds are perpendicular to the line of sight, and all of the radial velocities are zero. That is why the map in the previous figure is empty in the wedge-shaped region directly towards the center. Clearly we live in a spiral galaxy, but a spiral pattern appears to be slightly irregular, with many branches and gaps. The stars you see in Orion, for example, appear to be in a detached segment of a spiral arm, referred to as a spur. By combining observations of our own galaxy with studies of other galaxies, astronomers can make educated guesses about what a Milky Way galaxy might look like viewed from outside. And this is what we get. So the two-armed model of the Milky Way is based on observations with the Spitzer Infrared Space Telescope. And notice the large central bar. And here we can see branches and spurs are common in this model. In addition to helping map the arrangements of spiral arms, infrared observations indicate that a central bulge of our galaxy is not a sphere but rather an elongated bar pointing partially away from Earth. In the next chapter, you will see that such structures are common in other galaxies as well. One important fact revealed by radio maps is that the spiral arms are regions of high gas density. Spiral traces tell you that the arms contain young objects, so you suspect they must also have active star formation. Radio maps confirm your suspicion by telling you that the material needed to make stars is abundant and concentrated in spiral arms. Having mapped the spiral pattern of our galaxy and seen the patterns in other galaxies, you might ask, just what are spiral arms? You can be sure they are not physically connected structures like bands of magnetic fields that hold the gas in place. If they were, the differential rotation of a galaxy would destroy them within a few 100 million years, winding them up and tearing them apart, like paper streamers caught on the wheel of a speeding car. Yet spiral arms are common in galaxies, so they must last for billions of years. Astronomers conclude that spiral arms are dynamically stable. They retain the same appearance even though the gas, dust, and stars in them are constantly changing. You see how this works. Think of the traffic jam behind a slow-moving truck. Seen from an airplane, the traffic jam would be stable, moving slowly down the highway. But you could watch an individual car approach from behind, slow down, wait its turn, finally reach the front of the jam, passes the truck, and resume speed. The individual cars in the jam are constantly changing, but the traffic jam itself is a stable pattern, moving at its own speed along the highway. In a spiral density wave theory, spiral arms are dynamically stable regions of compression that move slowly around the galaxy, just as the truck moves slowly down the highway. Gas clouds moving at orbital velocities around the galaxy overtake the slow-moving arms from behind and slam into the gas already in the arms. The sudden compression of the gas can trigger the collapse of the gas clouds and the formation of new stars. Newly formed stars and the remaining gas eventually move on through the arm and emerge from the front of the slow-moving arm to resume their travels around the galaxy. So here we can see orbiting gas clouds overtake the spiral arm from behind. The compression of the gas cloud triggers star formation. Massive stars are highly luminous and make the spiral arm prominent. The most massive stars die quickly, so the OB stars. Low mass stars live long lives but are not highly luminous. What evidence do astronomers have that star formation is caused by spiral density waves? Spiral traces are the key. Stars of all masses are forming in spiral arms, but as you have already learned, the O and B stars live such short lifetimes that they die before they can move out of the spiral arm. These massive high luminosity stars, along with gas and dust, confirm that spiral arms are sites of star formation. You can expect that lower mass stars like the Sun can't be used as spiral traces. They also form in spiral arms, but during their relatively long lives, they leave the arms in which they were born. The Sun probably formed as part of an association in a star-forming region within a spiral arm almost 5 billion years ago, escaped from that association, and has circled the galaxy more than 20 times, passing through many spiral arms. Plotting the locations of Sun-like stars does not reveal the spiral pattern, confirming this picture. The evidence seemed to fit the spiral density wave theory well, but the theory has two problems. Firstly, how does the complicated spiral distribution begin, and how is it sustained? Computer models indicate that spiral density waves should slowly die out in about 1 billion years. So something must regenerate a spiral wave. Mathematical models show that a disk of the galaxy is naturally strongly affected by certain types of disturbances. As you learned earlier, observations show that the center of a galaxy is not a sphere but a bar. The gravitational effects of the bar's rotation could continuously perturb the galaxy's disk and stimulate the formation of spiral density waves. A close encounter with a passing galaxy could also stimulate a spiral pattern. Some galaxies without a visible bar or large companion nevertheless has prominent spiral arms. So astronomers continue to make observations and computer models, investigating the question of spiral arm formation. The second problem for density wave theory involved the spurs and branches observed in the arms of our own and other galaxies. Some galaxies, called grand design galaxies, have symmetric two-arm patterns. Other galaxies have a great many short spiral segments, giving them a fluffy appearance but no overall grand design. These galaxies have been termed flocculent, meaning woolly. Our Milky Way galaxy seems to be intermediate between extremes, or flocculent versus grand design. What process might make small-scale spiral segments instead of galaxy-wide spiral pattern? The answer may lie in self-sustaining star formation. So in image A, some galaxies are dominated by two spiral arms, but even in these galaxies, minor spurs and branches are common. Spiral density waves can generate the two-armed grand design pattern, but self-sustained star formation may be responsible for the irregularities. Then in image B, many spiral galaxies do not appear to have prominent spiral arms. Abundant spurs and branches nevertheless suggest that star formation is proceeding robustly in such galaxies. Observations include that our Milky Way galaxy's spiral pattern is intermediate between these two examples. So, the answer may lie in self-sustaining star formation. You learned in Chapter 9, Section 2, that star formation in one location can lead by supernova explosions, stellar winds, and outflows to star formation in neighboring location. The differential rotation of the galaxy will drag the inner edge of star-forming cloud ahead and let the outer edge lag behind. This will result in a region of star formation shaped like a segment of a spiral arm. This is spur. And here we get to this image again. So differential rotation drags the inner edge of a gas cloud ahead of its outer edge. So this edge is dragged faster than the outer edge. So a cloud can become elongated by continuing differential rotation. Star formation in gas clouds can produce massive stars who has high luminosity, so this is the O and B type stars. And supernova explosions can compress surrounding gas and trigger more star formation. If star formation continues long enough, a cloud can be elongated into a spiral segment. Astronomers suspect that while a spiral density wave can generate beautiful two-armed patterns, the self-sustaining star formation process produces the branches and spurs so prominent in some galaxies, including our own. These discussions of star formation in spiral arms illustrates the importance of natural processes. The spiral density wave creates graceful arms, but it is the star formation in the arms that makes them stand out so prominently. Self-sustaining star formation can act in some galaxies to modify the spiral arms and produce branches and spurs. In other galaxies, it can make the spiral pattern flocculent by searching out and understanding details of such natural processes. Astronomers can begin to understand the overall structure and evolution of the universe we live in. So now we're going to start looking at what is in the nucleus of a galaxy. And this is a research field completely on its own. I have a few colleagues that dedicate their lives to study the nucleus of galaxies. So the most mysterious region of a galaxy is its very center, the nucleus. At visual wavelengths, this region is totally hidden by dust and gas that dim the light it emits by 30 magnitudes. If 1 trillion photons of light left the center of the galaxy on a journey to Earth, only one of those photons would make it through the dust and gas. Consequently, visual wavelength images reveal nothing about the nucleus. Observations at infrared and radio wavelengths can see through the interstellar material, and those images show a region of tremendously crowded stars orbiting in the nucleus at high velocity. To understand what is happening in the innermost regions of our galaxy, you need to carefully compare observations and hypotheses. If you look up at the Milky Way on a dark night, you might notice a slight thickening of the direction of the constellation Sagittarius, but nothing specifically identifies this as the direction of the heart of the galaxy. Even Shapley's study of globular clusters identified the location only approximately. The first complete infrared map of the central bulge, made by Eric Becklin in 1968, showed the location of intense radiation where the stars are most crowded together. Radiation would have still more crowded together. The gravitational core of the galaxy. High-resolution radio maps of the stellar center reveal a complex collection of radio sources, with one Sagittarius A lying at the exact location of the galactic nucleus. Radio interferometer observations show that Sagittarius A is less than 1 AU in diameter, but nevertheless a strong source of radio energy as well as X-ray emissions. So are all of you still happy with the terminology of interferometer? Awesome. So there are 3 points to consider. Observations at radio infrared wavelengths reveal complex structures near Sagittarius A caused by magnetic fields and rapid star formation. Supernova remnants show that massive stars have formed there recently and exploded the ends of their lives. So, Mr. Visagi, what is meant with the interferometer is, with the interferometer, you have a lot of telescopes looking at the same object at the same time. Then you can correlate those data and see where everything differs. Or you can interferometer, use an interferometer, so interferometrate those signals, and you see what you get. So with an interferometer, you can basically do the same principle as, yes, the exact same thing in the slide of last week in that talk. Yes. And then, secondly, the center is crowded. Tremendous number of stars heat the dust, which emits strong infrared radiation. Then, thirdly, there is evidence that Sagittarius A is a supermassive black hole into which gas is flowing. Observations of the motions of stars orbiting the central object indicate its mass is about 4 million solar masses. A supermassive black hole is an exciting idea, but scientists must always be aware of the difference between adequacy and necessity. A supermassive black hole is adequate to explain the observations, but is it necessary? Could there be another explanation? For example, some astronomers have suggested that the gas flowing inward could trigger tremendous bursts of star formation, causing some of the turmoil observed in the galactic nucleus. Such hypothesis has been considered and tested against the evidence, but none appears to be adequate to explain all the observations. So, for the only viable hypothesis is that our galaxy nucleus is home to a supermassive black hole. Meanwhile, observations are allowing astronomers to refine their models. For instance, Sagittarius A is not as bright in X-rays as it should be if it has a hot accretion disk with matter constantly flowing into the black hole. Observations of X-ray and infrared flares lasting only a few hours suggest that the mountain-sized blobs of matter may occasionally fall into the black hole and be ripped apart and heated by tides. The black hole seems to be mostly dormant, lacking a fully developed hot accretion disk because little matter is flowing into it at present time. Such a supermassive black hole could not be the remains of a single dead star. It contains too much mass. It probably formed when the galaxy first formed over 13 billion years ago. In later chapters, you will see that such supermassive black holes are found at the centers of most large galaxies. Just as dinosaurs left behind fossilized footprints, our galaxy has left behind clues about its youth. Astronomers have compelling evidence that the stars of the spherical component are old, must have formed long ago when the galaxy was very young. Some of that evidence comes from comparing abundances of chemical elements in stars located in different parts of the galaxy. The element building process. You can recall what you have learned about stellar structure and stellar evolution in previous chapters to understand the chemical evolution of the galaxy. In astronomy jargon, the term metals refer to all the chemical elements heavier than helium. So that's I'm sure you have seen a lot of memes about this before. But to keep this in mind, if you study galaxies and galaxy evolution as a whole, that forms part of a branch of astronomy called cosmology. So cosmology usually studies the galaxy as a whole and galaxy evolutions and compare galaxies to other galaxies. In a later chapter, you will learn about evidence that when the universe began, it contained about 90% of hydrogen atoms, 10% helium atoms, and little or no metals. The first stars that formed early in the universe's history therefore had to be nearly pure hydrogen and helium. All of the other chemical elements have been produced by nucleosynthesis, the process in stars that fuses hydrogen and helium to make the heavier atoms. As you already know, medium mass stars like the Sun cannot ignite carbon fusion, but during helium fusion, the heat and density can trigger some nuclear reactions that cook the gas to produce small amounts of elements heavier than helium. When the aging star pushes away its surface layers to produce a planetary nebula, some of those elements are spread back into the interstellar medium, where they may become part of newly forming stars and planetary systems. The most massive stars fuse elements up to iron and simultaneously cook the gas in their cores to produce small amounts of many different atoms, including sulfur and calcium. When those stars die in supernova explosion, traces of those elements are spread back into the interstellar medium, along with the rarer atoms such as gold, platinum, uranium produced in supernova explosion itself, which can also be incorporated eventually into new stars and planets. Nevertheless, metals are quite rare in the universe. Conventionally, astronomers graph the abundance of the elements using an exponential scale. But if you replot the data using a linear scale, you can see how rare these atoms are. So here we can see the abundance of chemical elements in the universe in figure A. When the elemental abundances are plotted on an exponential scale, you see that elements heavier than iron are about 1,000,000 times less common than iron, and that all elements heavier than, So that all elements heavier than iron are about 1,000,000 times less common than iron, and that all elements heavier than helium, the metals, are quite rare. Then in image B, the same data plotted on a linear scale provide a more realistic impression of how rare the metals are. Carbon, nitrogen, oxygen make small peaks near the atomic mass 15, and the peak representing iron is just visible in the graph. So, gentlemen, I see is up. We'll do this lecture tomorrow evening. I will still be available tomorrow evening to answer more questions for preparation for the semester test. So thanks for a great evening. Thank you for participating in the semester test. And you're more than welcome to log off, and I will see you all tomorrow evening.